Welcome back to Ubad's lab, and today we're going to be calculating escape speed. Alright, first I gotta start this video off with an apology. Haven't posted in around 2 weeks, so I'm sorry about that. I've been a little busy, but we're back here now, and I got a fun problem for you guys, which is an escape speed problem that has to do with gravitation. So let's say we have a planet over here. Let's draw a diagram. This is our planet, and around that planet we have a satellite, which we did this. That's going around this planet in a circular motion, and its centripetal acceleration is gravity. That's what's keeping it in this orbit. So the gravity from this planet is the force that's keeping this planet in this circular motion. That's keeping the satellite in this circular motion. And so we want to find in this problem what is the minimum speed needed for this satellite to escape the gravitational pull of this planet and get far enough so that there's no gravity acting upon the satellite from this planet, and it'll eventually get pulled out. So let's say like the speed isn't great enough, it'll get like kind of outside of this orbit, and then it'll still be close enough so that this gravity will just pull it back, and it'll just end up in an orbit again. So we want to find the minimum speed to escape this gravitational pull. So we have to find we have to use something crucial to know about escape speed. We know that once this object has escaped its the gravitational pull of this planet, the potential energy from gravity from this planet has to be equal to 0. Since if the potential energy wasn't 0, then it'd get pulled back. There's some type of energy force pulling it back over here. So and then another thing that we need to know is that K will equal to 0 once this planet has escaped the gravitational pull. That one's a little harder to understand. A good way to think about it that my physics teacher put it was that let's say like you're trying to escape out of a hole in the ceiling. Like the minimum velocity that you need to escape and jump out from that hole in the ceiling, and that minimum velocity, what speed are you gonna have when you're just made it out? You're gonna be at 0 because you go up and then you stop, right? So you kind of just make it out. So it's so the K equals 0 is kind of because we're looking for the minimum velocity to escape. So it'll make it out, and then it'll just make it out of the gravitational pull, and then it'll stop moving because then its kinetic energy will be 0. So we can set up a conservation of mechanical energy here. So we have U plus K. Potential energy plus kinetic energy is equal to U plus K. So before and after. So at this point where it is right now, and at the point where it's way, way out there and escaped the orbit. So we can set both of this side to 0. So we'll do that after doing this side. So what's the potential energy of this object over here? So potential energy is negative. For this one it's negative, and it's G. G is our gravitational constant, which is around 6.67 times 10 to the negative 11th universal gravitational constant. And so it's going to be G times, this will be M1, this will be M2 for the mass. You know, I love my variables. We're going to stay away from numbers here. So G, M1, M2 over R believe it's just over r. Okay, which is our radius from here to here at this point. That's an r. That might look like a v. So it's this, right? And we add our kinetic energy, which is 1/2 mv squared. We know that. So it will be 1/2. Is it the mass of the planet or the mass of the satellite? It is the mass of the satellite, because that's what has the kinetic energy. That's what's trying to move away. So it's 1/2 m2v squared. And that's all equal to 0, since potential and kinetic energy will be 0 once it has escaped the orbit. So what do we want to solve for? We want to solve for v, which is right there. So what can we do to solve for that? We can add this whole term to the other side. So let's add that whole term to the other side. So we have 1/2 m2v squared is equal to g m1 m2 over r. And then there's m2, boom, boom. Divide one of them to the other side. And then we can multiply both sides by 2 and then take the square root. So our final answer for our v escape will equal to rad. We multiplied the 2 over inside. So 2g m1 over r. All right, so that is our escape speed, or minimum velocity needed to escape the orbit in terms of constants, which, such as 2 and g, and m1, which is the mass of our planet, and the radius between the satellite and the planet. And what's interesting is that m2 actually does not play a role in the speed needed to escape. So it doesn't matter how big this satellite is, which is pretty interesting to think about. And yeah, that's the problem.